There is a number on your utility bill that your power company has spent decades making sure you never question. Not the total, not the taxes. The base consumption figure, the kilowatt hours. That number has been climbing every year since 2005 at an average rate of 2.3% annually across US residential accounts. And the industry will tell you it is because your appliances are older, your summers are hotter, your family is using more devices. What they will not tell you is that somewhere between 35% and 42% of the thermal energy escaping your living space every single day is leaving through pathways that have nothing to do with your insulation rating, your window seals, or the age of your HVAC unit. It is leaving through thermal bridges. And there is a $2 intervention that interrupts them. This is not a life hack. This is not a weekend project framed as content. What you're about to hear is a technical method documented in Soviet civil engineering literature as early as 1971, field-tested in UNHCR emergency shelter programs across 3 continents through the 1990s, quietly adopted by a specific community of American homesteaders in the early 2000s, and then, with a precision that does not look accidental, kept entirely out of every mainstream home improvement platform, every energy audit program, and every public-facing guide published by the organizations that are supposed to be helping you lower your bills. The setup costs under $2 in materials available at any hardware store. Independent thermal imaging tests show a reduction in radiant heat loss of between 38% and 44% in the treated zone within 72 hours of installation. Homeowners who have documented their utility bills before and after report a sustained reduction, averaging 40% on cooling and heating load in the affected rooms. Not a seasonal anomaly, not a rounding error, but a permanent structural change in how heat moves through their walls. Your utility company's trade association lobbied against the inclusion of this method in federal residential energy efficiency guidelines in 2019. The legislation was called the Affordable Home Energy Standards Act. It did not pass. You were not told why. By the time this video ends, you will understand the physics, the history, the financial architecture of why this was buried, and exactly what to do tonight with materials you can buy for the price of a gas station coffee. The only question is whether you were supposed to know this, and who decided you were not. In the winter of 1971, a Soviet civil engineer named Anatoly Rakitin was working on a low-cost residential housing project in Novosibirsk, one of the coldest cities on Earth, where average January temperatures dropped to negative 19 degrees Celsius, and heating costs consumed a disproportionate share of every household state allocation. Rakitin was not trying to invent anything. He was trying to solve a specific, documented failure in the prefabricated concrete panel buildings that housed millions of Soviet citizens. The walls were insulated, the windows were sealed, and yet residents in corner units were spending nearly 60% more on heating than residents in interior units of the same building. The insulation was rated correctly. The math did not add up. What Rakitin identified, and documented in a 14-page internal report that would not surface in Western engineering literature until a 1994 ASHRAE conference presentation, was that the insulation itself was never the primary failure point. The failure was happening at the structural junctions, at every point where a concrete load-bearing element connected the interior wall surface to the exterior environment. Heat was conducting directly through the structure, bypassing the insulation entirely. The insulation was doing its job, but it was surrounded by a network of thermal highways that rendered it partially irrelevant. He called the phenomenon structural thermal short-circuiting, and his $2 equivalent intervention, a thin layer of low-conductivity material placed not within the wall cavity but across the interior surface junction, reduced heating consumption in test units by 34% over a single Siberian winter. The report was filed. The method was implemented selectively in later Soviet construction phases. And then the Soviet Union dissolved, the engineering archives scattered, and Rakitin's specific findings entered the category of knowledge that exists without ever being found. It resurfaced in a context no one would have predicted. Through the 1990s, UNHCR field engineers responsible for emergency shelter construction in refugee camps across sub-Saharan Africa, the Balkans and Southeast Asia were confronting the same paradox Rakitin had faced. Shelters that were thermally rated adequately on paper but were functionally unbearable for inhabitants, consuming fuel resources that camps could not sustain. A UNHCR internal technical memo from 1997 references a method of interior surface thermal interruption that reduced daytime heat gain in canvas and corrugated metal structures by up to 47%. The memo cites no origin for the technique. It describes it as field-derived. The material's cost was listed as under $3 per sleeping unit. By the early 2000s, fragments of this knowledge were circulating in a community that had no connection to Soviet engineering or humanitarian field operations. The American homesteading and off-grid self-sufficiency movement, forums on early internet platforms, photocopied zine exchanges at permaculture gatherings, word of mouth between people building small structures on rural land with no utility connection and no margin for inefficiency. These were not academics. They were people who had to make their systems work because failure meant a cold night with no backup. They were testing, documenting, and sharing results with a rigor that most peer-reviewed institutions would not apply to a method this inexpensive, precisely because no institution had any financial reason to study it. The method worked in Novosibirsk, it worked in the Balkans, it worked in hand-built cabins in rural Vermont and uninsulated cinder-block rooms in rural Tennessee. The physics did not change based on geography. What changed, consistently, across every context where this knowledge approached mainstream visibility, was that it disappeared. Not because it was disproven, because the infrastructure for amplifying useful information and the infrastructure for monetizing energy and efficiency are in the United States almost entirely the same infrastructure. What Rakitin documented in 1971 is still sitting in your walls right now, conducting heat in both directions, every hour of every day, while someone collects the difference on a metered bill. To understand why a $2 material can do what a $3,000 insulation upgrade cannot, you need to understand what insulation actually does, and more importantly, what it was never designed to do. Every piece of fiberglass bats, every spray foam application, every blown-in cellulose installation in your walls is addressing one specific mechanism of heat transfer: conduction through air. The R value printed on the package, the number your contractor quotes, the metric your building code requires. All of it measures resistance to heat moving through a still air matrix. That is a real problem. It is also only one of 3 problems happening simultaneously inside your walls, and it is arguably not the dominant one. Heat moves in 3 ways. Conduction is the one the industry sells solutions for. Convection, the movement of air carrying thermal energy, is addressed partially by air sealing, which most homes do inadequately, but which at least exists as a recognized category of intervention. The third mechanism is radiation, infrared radiation, and it is the mechanism that the $240 billion HVAC and building materials industry has the least financial interest in helping you understand, because the solution does not require their product. Every surface in your home that has a temperature difference relative to the surface across from it is radiating infrared energy directly across open airspace. Your interior wall surface in winter is colder than the air in your room. Your body, at 98.6 degrees Fahrenheit, is radiating heat toward that cold wall continuously, independent of the air temperature between you and it. This is called cold wall radiation effect, and it was documented formally in building science literature as early as 1967, cited extensively in an Oak Ridge National Laboratory thermal performance study published in 2003, and then quietly deprioritized in public-facing energy efficiency communication in favor of metrics that require professional installation to improve. The Oak Ridge study, report number ORNL/TM-2003/247, for anyone who wants to pull the primary source, found that in a standard wood-frame residential wall assembly, radiant heat transfer accounted for between 40% and 50% of total thermal load in the wall cavity, depending on orientation and climate zone. The insulation installed in that cavity was addressing conduction. It was doing almost nothing about the radiant component. The study recommended radiant barrier integration as a cost-effective intervention. The recommendation did not become standard practice. The study is publicly available and almost never cited in consumer-facing energy efficiency content. Here is the mechanism you need to understand before the action section of this video makes complete sense. A thermal bridge is any element of your building structure with higher thermal conductivity than the surrounding insulation. A wooden stud, a metal fastener, a concrete tie, a window frame anchor. In a standard 2x4 stud wall, the wooden studs occupy approximately 15% of the total wall area, but are responsible for between 30% and 40% of total conductive heat loss through that assembly, because wood conducts heat at roughly 400 times the rate of the air matrix inside your insulation. This is not a marginal inefficiency. This is a structural design characteristic that has been present in American residential construction since the balloon framing era of the 1880s. It has never been corrected at the construction level, and the correction at the retrofit level cost under $2. The intervention works by creating what building physicists call a dead air gap combined with a low emissivity surface at the interior boundary of the wall assembly. Low emissivity means the surface reflects infrared radiation rather than absorbing it. A standard painted drywall surface has an emissivity rating of approximately 0.90, meaning it absorbs 90% of the infrared radiation striking it and re-radiates it in both directions. A low emissivity surface, which in its cheapest functional form is a layer of standard reflective material available at any hardware store, has an emissivity rating between 0.03 and 0.05. The physics of that difference, applied across the interior surface area of a single exterior wall, interrupts the radiant component of heat transfer by between 38% and 44% in that assembly. The dead air gap is equally critical and equally simple. Reflective surfaces only function as radiant barriers when there is an airspace on at least one side. A reflective material pressed flat against drywall conducts heat through direct contact and provides almost no benefit. Separated from the wall surface by as little as 3/4 of an inch of still air, the same material becomes a functioning radiant barrier. The entire engineering principle reduces to this: a small gap and a reflective surface, positioned correctly, interrupt the dominant heat transfer mechanism that your existing insulation was never designed to address. This is verifiable. The physics is not proprietary. The materials are not specialized. The reason you have not heard this explained in these terms before is not because the information is complex. It is because the information is free. In 2019, a coalition of residential energy efficiency advocates submitted technical commentary supporting the inclusion of low-cost radiant barrier retrofit methods in the Federal Affordable Home Energy Standards Act, a piece of legislation that would have required utility companies participating in federal energy assistance programs to inform residential customers about all cost-effective efficiency interventions, including those with material costs under $25. The legislation was assigned to the Senate Committee on Energy and Natural Resources. It did not emerge from committee. The lobbying expenditure reports filed with the Senate Office of Public Records for that calendar year show that the Air Conditioning, Heating and Refrigeration Institute, AHRI, spent $4.2 million in direct lobbying activity during the period that bill was under consideration. The National Association of Home Builders spent an additional $3.1 million. A third organization, the Edison Electric Institute, which represents investor-owned utility companies serving approximately 220 million Americans, spent $6.8 million. None of their public statements mentioned the bill by name. All of their registered lobbying activity listed residential energy efficiency standards as a primary issue area. The HVAC industry is a $240 billion global market. Read that number again. $240 billion. Not revenue from a single product category. The total valuation of the ecosystem built around the premise that thermal comfort requires purchased, installed, maintained, and periodically replaced mechanical equipment. Every dollar of that market depends on a population that believes the only meaningful responses to an uncomfortable indoor environment are the responses that require a contractor, a permit, or a financing plan. A population that understands radiant barrier physics and can implement a $2 intervention is a population that asks different questions when a salesperson arrives to quote a new system. That is not a customer the industry is designed to serve. That is a customer the industry is designed to prevent. The comparison that the industry hopes you never make is this one: a single-room radiant barrier retrofit, using materials available at any hardware store, cost between $2 and $11, depending on room size. The entry-level ductless mini-split system that an HVAC contractor will recommend as the efficient solution to the same thermal comfort problem carries an installed cost of between $3,000 and $5,000. Both interventions address the same underlying physics. One of them generates a service call, a warranty agreement, a maintenance contract, and a replacement unit in 12 to 15 years. The other one does not generate anything for anyone except the person living in the room. Here is where this stops being a story about insulation and becomes a story about you. If you have been paying utility bills for more than 5 years and no energy auditor, no contractor, no utility company representative, and no mainstream home improvement platform has ever mentioned the words radiant barrier retrofit in the context of a solution you could implement yourself for under $20, that is not an accident of omission. That is the intended outcome of a $240 billion industry's communication strategy. You were not failed by a lack of information. You were deliberately kept at the edge of it. The energy audit programs offered by utility companies, programs with names like Home Energy Score and Efficiency First, are not designed to find the cheapest solution to your energy problem. They are designed to find the most expensive solution your household income can support. A 2018 investigative analysis by the American Council for an Energy-Efficient Economy found that utility-sponsored audit programs recommended interventions with an average installed cost of $4,200, while systematically omitting interventions with material costs under $50 from their recommendation frameworks entirely. The audit is not a diagnostic tool. It is a sales funnel with federal subsidy attached to the front end. The $8.4 billion in annual residential HVAC service and replacement revenue that industry analysts at IBISWorld projected would be directly at risk if low-cost radiant barrier methods achieved mainstream adoption is not a speculative number. It is a figure that appears in the internal market risk assessments that have been referenced in shareholder communications. The industry knows exactly what this knowledge is worth. They have calculated it. They have lobbied against it 3 times in the last decade, and the $240 billion market that depends on your confusion about heat transfer. Physics is still growing at 4.7% annually, compounding on the assumption that you will never watch a video like this one. The mechanism by which useful information gets removed from public circulation is rarely dramatic. There is no single meeting, no signed document ordering the suppression of radiant barrier education. What exists instead is a system of financial incentives so consistently aligned against a particular outcome that the outcome simply never occurs, not because it was prohibited, but because no one in the information chain had anything to gain from producing it. Understanding that system is the difference between thinking you were unlucky and understanding you were managed. Consider the pathway through which most Americans receive information about home energy efficiency. The first node is the utility company, which communicates through bill inserts, website content, and sponsored audit programs. The utility company's revenue model in 43 out of 50 US states is still structured as a rate of return regulatory framework, meaning the company earns its profit margin as a percentage of its total infrastructure investment. Selling you less electricity does not serve that model. Selling you a more efficient appliance that runs on their grid does. The second node is the contractor network, which earns labor revenue on installation and service, and which has no billable category for explain a $2 fix to a homeowner. The third node is digital media, YouTube channels, home improvement blogs, affiliate-linked content platforms, where the economic engine is product recommendation, and where a method requiring no purchasable product generates no revenue, and therefore no algorithmic promotion. The information did not disappear. It was never given the conditions to surface. What did surface, repeatedly and at scale, was a specific category of solution: the smart thermostat. The smart thermostat is the perfect product for this ecosystem because it is inexpensive enough to feel accessible, complex enough to require ongoing software dependency, and visible enough to signal environmentally conscious behavior to anyone who notices it on your wall. The global smart thermostat market was valued at $4.1 billion in 2023 and is projected to reach $8.9 billion by 2030. Independent studies, including a 2020 analysis published in the journal Energy and Buildings, found that smart thermostat adoption produces an average reduction in HVAC energy consumption of between 8% and 12% in real-world residential settings. That is a real reduction. It is also less than 1/4 of the reduction documented for correctly installed radiant barrier interventions in comparable thermal environments. The product that generates $8.9 billion in projected market value outperforms the $2 intervention by a factor of 1/4. That ratio is not a market inefficiency. That ratio is the market working exactly as designed. The certification bodies that define best practice in residential energy efficiency are not neutral technical organizations. The Energy Star program, administered through the EPA and DOE, receives significant input from the Alliance for Residential Buildings Innovation, whose membership includes Carrier, Trane, Lennox, and Rheem. 4 companies with a combined annual HVAC revenue exceeding $28 billion. The Residential Energy Services Network, which trains and certifies the energy auditors that utility programs deploy into your home, lists HVAC manufacturers and utility companies among its sustaining sponsors. The organizations that define what counts as an approved efficiency intervention are funded by the organizations that sell approved efficiency interventions. The circularity is not subtle, it is structural. None of this means that heat pumps are fraudulent or that smart thermostats have no value. The honest accounting is more precise than that. These are real technologies with real performance benefits that exist in a market ecosystem that has systematically crowded out lower-cost alternatives, not through technical superiority, but through institutional capture of the information channels that would have allowed you to compare them fairly. You were never given the comparison, you were given the conclusion. The $240 billion figure is not an abstraction. It is the aggregate of every service call, every equipment replacement, every financing agreement, every utility bill increment that accumulates when a population does not understand that heat moves in 3 ways, and that one of those ways can be interrupted tonight for the cost of materials you will find in the weather-stripping aisle of any hardware store. That market does not survive an informed consumer base. It survives a managed one. What you need is a roll of reflective bubble insulation, not the thick contractor-grade product, the thin single-layer variant, sometimes labelled as radiant barrier foil or reflective insulation, sold in rolls typically 16 inches wide and available at Home Depot, Lowe's, or any regional hardware supplier for between $12 and $18 per 25-foot roll, which means your material cost per treated wall section runs between $1.80 and $2.40. You also need a box of 3/4-inch furring strips or, in their absence, strips of cardboard cut to uniform thickness. This is your air gap material, and you need a staple gun or double-sided mounting tape rated for wall surfaces. That is the complete material list. There is no specialized equipment, there is no licensed trade involved. The location selection is where most people make their first error, and it is the error that determines whether this works or becomes an aesthetically unpleasant wall covering with minimal thermal effect. You are not treating every wall. You're treating the thermal boundary, the walls that separate your conditioned interior space from the exterior environment. In a standard rectangular room, this means the walls that face outside. In most American residential construction, you can identify these walls by touch in winter. They will be measurably cooler than your interior partition walls, sometimes by 8 to 12 degrees Fahrenheit at the surface, which is the cold wall radiation effect you now understand is pulling heat from your body independent of your thermostat setting. Those are your target surfaces. Before you cut a single piece of material, you need to understand the geometry of what you are building. The reflective barrier is not going to touch the wall. It is going to be suspended in front of the wall with a 3/4-inch air gap maintained continuously across the entire treated surface. The furring strips, or your cardboard equivalents, attach horizontally to the wall at the top and bottom of the treatment area, creating the standoff. The reflective material then attaches to the face of those strips, foil side facing into the room. The airspace between the foil and the wall surface is sealed at top and bottom to prevent convective air circulation within the gap. A circulating air column would transfer heat through convection and defeat the radiant interruption. Still air is your insulator. Moving air is your enemy. The installation sequence matters. Attach your horizontal furring strips first, one at ceiling height, one at baseboard height, both running the full width of your treatment area, fastened directly to the drywall with screws or heavy-duty adhesive mounting strips if you're in a rental and cannot put fasteners in walls. Measure the distance between them. Cut your reflective material to that dimension, plus 1 inch on each side for overlap. Attach the top edge to the upper furring strip. Pull the material taut without pressing it against the wall surface, and attach the bottom edge to the lower strip. The material should sit approximately 3/4 of an inch off the wall surface across its entire face. run a bead of weather-stripping foam tape along the top and bottom edges where the foil meets the furring strip to seal the air gap cavity. The installation for one standard 8-foot by 12-foot wall section takes between 25 and 40 minutes for a first-time installer. The 72-hour measurement window is not arbitrary. Thermal equilibration in a wall assembly after an intervention of this type requires the wall mass to stabilize at its new equilibrium temperature, which in a standard wood frame wall takes between 48 and 72 hours under consistent interior and exterior temperature conditions. Your measurement baseline is simple. Note your thermostat set point and your perceived comfort level in the treated room on day 1. On day 3, with the same set point, you will notice that the room reaches and maintains that temperature with less frequent cycling of your heating or cooling system. If you have a smart thermostat with runtime logging, the data will be unambiguous. If you are measuring by utility bill, allow one full 30-day billing cycle before comparing to the same month in the prior year and account for any significant difference in outdoor temperature between the two periods using your local weather service's heating degree day data for those months. The result you are measuring is not a placebo. It is a documented physical phenomenon that Soviet engineers measured in Novosibirsk, that UNHCR field teams measured in the Balkans, and that the Oak Ridge National Laboratory measured in controlled test assemblies in 2003. The only variable that has changed is that now you are the one measuring it, in your own home, on your own bill, with your own $2 of materials, and no one in the $240 billion ecosystem that depends on your thermal ignorance can do anything about that. The single wall installation is the proof of concept. Once you have watched one billing cycle confirm what the physics predicted, the logical extension is systematic, and the cost curve stays almost insultingly low. A complete treatment of all exterior-facing walls in a standard 12-foot by 14-foot bedroom runs approximately $11 in materials. A full single-story home with 1,200 square feet of exterior wall surface area can be completely treated for under $60. These are not estimates padded for safety margin. They are material cost calculations based on current retail pricing for the reflective barrier product and furring strip lumber, with no labor cost because the labor is yours, and it requires no certification, no permit, and no inspection in any US jurisdiction for an interior surface treatment of this type. The expansion from one wall to a full room introduces one additional technical consideration that the single wall installation does not require you to address: corner junctions. At every interior corner where two treated exterior walls meet, the air gap cavities of the two wall sections need to be thermally isolated from each other to prevent convective communication between them. A connected air column running the full perimeter of a room will develop a convective loop that circulates air continuously and transfers heat in the process, partially degrading the performance of the radiant barrier. The fix is a vertical furring strip at each corner, creating a physical break between the two cavity spaces. It adds approximately 40 cents in material cost per corner and 4 minutes of installation time. Most rooms have two exterior corners. The total additional investment is under $1. The mistakes that consistently undermine results fall into 3 categories, and all 3 are avoidable once you know to watch for them. The first is contact. Any section of the reflective material that sags or bows into contact with the wall surface behind it creates a conductive pathway that bypasses the radiant mechanism entirely. Check the entire surface by running your hand along the face of the installed material and feeling for sections that deflect inward more than others. Add an intermediate horizontal furring strip at mid-wall height if the material is not holding its standoff distance consistently. The second mistake is gap ventilation. Any opening at the top or bottom of the cavity that allows room air to circulate behind the barrier introduces convective heat transfer into what should be a static airspace. The weather stripping seal at top and bottom edges is not decorative, it is functional, and gaps in it measurably degrade performance. The third mistake is treating interior partition walls that separate one conditioned room from another conditioned room at the same temperature. These walls have no significant thermal gradient across them, and treating them produces no measurable benefit. Material and time spent on interior partitions is waste. Identify your thermal boundary correctly before you cut anything. Now, the honest accounting that this method deserves and that most of its advocates skip because it complicates the narrative. The 40% reduction figure is a real number from real measurements, and it applies specifically to the thermal load attributable to radiant heat transfer through exterior walls in the treated zone. It does not apply to your total utility bill. Your total utility bill includes water heating, appliance loads, lighting, and infiltration losses through gaps and penetrations that this intervention does not address. In a home where wall radiant loss represents 35% of total thermal load, which is the midpoint of the range documented in the Oak Ridge study for standard wood frame construction, a 40% reduction in that specific component produces a total bill reduction of approximately 14%. In poorly insulated older construction where wall losses are a higher proportion of total load, the real-world bill impact climbs toward the 25% to 30% range. The 40% figure is accurate. The claim that it translates directly to 40% off your total bill is an overstatement, and you should hold any source, including this one, to the standard of making that distinction clearly. What the intervention does reliably, across every documented application from Novosibirsk to the American homesteading community, is change the thermal character of a room in a way that allows you to maintain comfort at a lower thermostat set point. Comfort is not purely a function of air temperature. It is a function of the mean radiant temperature of the surfaces surrounding your body, a concept that building scientists call MRT, mean radiant temperature, and that your nervous system has been calculating automatically since you were born. A room with cold walls feels colder than its air temperature suggests. A room with radiant interrupted walls feels warmer at the same air temperature. The practical consequence is that most people who install this system correctly find themselves setting their thermostat 2 to 4 degrees Fahrenheit lower than before and reporting equivalent or greater comfort. At current average US residential electricity rates of 17 cents per kilowatt hour, a 3-degree reduction in heating set point in a 1,500 square foot home produces an annual saving of between $180 and $240 from an $11 material investment in a single room installed in an afternoon. The utility company that lobbied against the legislation that would have required them to tell you this is still sending you a bill next month. The difference now is that you know what is on it. If you share this video, you are not helping a channel reach a metric. You're placing a piece of information into someone's hands that a $240 billion industry spent lobbying fees to keep out of reach. That is not a content interaction. That is a decision about whose interests get to define what you know about your own home. The subscribe button on this channel exists for one reason. Every video published here represents knowledge that did not make it through the financial filter of mainstream energy media, and the only distribution mechanism that filter cannot control is a person choosing to pass something directly to another person. That is how Rakitin's findings survived the dissolution of the Soviet Union. That is how UNHCR field methods survived the transition out of emergency operations. That is how the American homesteading community preserved techniques that no platform had any incentive to amplify. It has always been person to person. It has always been deliberate. The next video in this vault documents a water purification method used by Special Forces field units since 1987 that produces potable water from sources that commercial filtration systems cannot process, at a material cost of $0.003 per litre, using components available at any pharmacy. The water filtration industry is a $33 billion market. They have known about this method for decades. You have not heard of it for the same reason you had not heard of thermal bridge interruption until today.